Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to Lesson 14-2, where we're still playing with logarithms. We just barely started with logarithms, right? You've just barely learned about a logarithm. You just barely learned that a logarithm is the inverse of an exponential function. And you've even learned that because they're inverses, how to go from one to the other and back again. So today we're going to talk a little bit more about logarithms and exponential functions and their graphs and their tables and how we write them, all that good stuff. So we're on student activity sheet 2, but we're all the way over on question number 10 to get this party started. And we're going to start off with questions 10 and 11. So we're starting off with the exponential equation of Red's fire ants, which is how we began this unit. So remember we had our table. Remember we said the fire ants was an exponential function. F equals 20 times 2 to the W power, where 2 is our base, W is our exponent, 20 is our coefficient, and well, F is the guy all on his own. Ha! And of course, we had the graph to go with that. So here's what I'd like us to do. I'd like you to take a few moments, and I'd like you to jot down your thoughts on questions 10 and 11. First of all, question 10, let's look at the domain and the range. And notice we're asking about the domain and the range of the function, as well as the domain and the range of the problem situation. Okay, two slightly different things. And of course, we are noticing as well that exponential functions have a horizontal asymptote. So I'd also like you to give me the equation for the asymptote of the function's graph. Go ahead and hit pause. Jot down your thoughts on questions 10 and 11, and then hit play when you're ready to continue the discussion. All right. You have a lot of space on your paper on number 10. I don't have as much space, and I don't like what they put here. So I'm going to write it out. Hey. So let's start off. We talked about the problem, and we talked about the function. So I'm going to talk about the problem situation over here with Red and his fire ants. But we're also going to talk about the entire function as well. So I'm going to put that over here. We put the fun in function. Yes, we do. All right. Pop that there. Junction. What's your exponential function? All right. So let's talk domain. In this case, domain is the number of weeks, all that good stuff. Now, you can see that my domain is my X, it's my number of weeks, my W, however you want to think of it. And as far as the function goes, I can plug in anything I want, right? Negative, positive, everything in between. Hey. So for my function, I would say that my domain, make a little note of this, my domain would be all real numbers. So you could write out all real numbers. You could say negative infinity to positive infinity, right? All that good stuff. The only thing is, as far as the problem goes, though, my domain is a little bit different. Because if my domain is the number of weeks, I start off at 0 weeks, right? I don't have negative weeks. I don't know what negative weeks would look like. So for my domain, I would say, for my problem, I would say that the domain is 0 to infinity until the fire ants take over the world and we're all dead. Sorry, that was a little morbid. They won't take over the world. We're fine. So while the domain of the function is all real numbers, the domain of the problem is all real numbers greater than 0. We don't have negative weeks. Let's talk about the range then. So my range, and again, we'll start with a function. And if I'm looking at the graph, remember that range is the y. Oops, except that I can't spell range. Haha, I fixed it. You won't even know the difference. So range is the y, and it looks like it doesn't quite get to 0. It gets really close to it, but it never actually gets to 0, and then just goes forever up from there. So I'm going to say my range is all real numbers greater than 0. So I'm going to do 0 to infinity. Ha, 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 ha. So for my function, my range would be from 0 to infinity, or all real numbers greater than 0. Now, the problem, though, is a little bit different, because we did not start off with 0 fire ants, right? I mean, Red had to start off with some fire ants in order to make more fire ants. You have to have fire ants to make more fire ants. They don't just magically appear. And in this case, red started off with 20 fire ants, which you can see started off with 20, and then it went up from there. So I would say my range for the problem situation for red and his fire ants would be all real numbers greater than or equal to 20. And notice it can be equal to 20, so I put a little bracket there instead of parenthesis. So they're very similar, but because of the practicality issues, like I'm not going to have a negative domain. I don't have negative weeks. And of course, we started off with 20 fire ants. I'm not going to have 0 fire ants. I started off with 20 fire ants, so that's why it looks a little different here. So one last little note question. So there's question number 10. I hope that helped clarify a little bit. Question number 11. What is the equation for the asymptote of the graph? Well, it looks like my asymptote is right down here. Ha ha! When my number of fire ants is 0. It reaches for 0, but it never actually gets there. So I'm going to say that my asymptote is f equals 0. My function gets super close to it. You could even say y equals 0 if you wanted to. My function gets super, super close to it, but it never actually gets there. So that would, of course, be my asymptote. Yay! Let's go to the next question. By the way, do you notice I figured out how to clear the whole page at once? Oh, I'm so smart. Let's go over to questions 12, 13, 14, and 15. I got a whole bunch of them here for you because, of course, this has to do with the inverse. This is about the logarithms. And I do have a whole bunch of questions for you here on your logarithms, which makes sense that I got more here because, of course, logarithms is the point of this unit. So to start off with, I have a bunch of questions. First of all, remember how we rewrote our exponential function as a logarithmic function? Do you remember this? We rewrote it like this with our fire ants. Remember, we switched our x's and our y's, which means we also switched our x-axis and our y-axis. And that means we also got a reflection for our graph. Our graph curved and shifted a little bit. We knew all that was going to happen. We did that last time. So here's what I would like you to do. Question number 12. Can you compare the domain of the logarithmic function and the domain of the problem situation, like last time? Question number 13, do the same thing with the range. Talk about the range of the function rule and compare that to the range of the problem situation. Question number 14, which you do have to flip the page. Question number 14, does the graph have an asymptote? And if so, where is it? So go ahead and hit pause to answer all your questions and then hit play when you're ready to check your work. All right, let's do this thing. Let's start off with the domain. I need my pen. All right, we'll start off with the domain. So we're talking about domain here. So let's talk about the domain. And we wanted to compare the function as compared to the actual problem situation. So do you remember, you might want to flip over to the last 3 problems we did, because do you remember that a logarithm is the inverse? It's the inverse of your exponential function. Does it inverse mean you're switching your x and your y values? Doesn't inverse also mean that you're swapping your domain and your range? Oh, that's right, people. Once we go to the logarithm, we've swapped our domain and our range. So for the problem situation, we said that for the problem situation, when it was an exponential, the domain was 0 to infinity, and the range was 20 to infinity. Well, that means that for the inverse then, and you can see here, this is my x. I start at 20 and I go forever to the right. So I'm going to say, all right, for the problem situation, it's 20 to infinity. But for the function situation, and again, it's just going to be swapped. It's going to be the range on the exponential is now our domain on our inverse. Boom. Could be the range of our domain of our logarithmic. Notice how that almost gets to 0, but never actually gets there and then goes forever up. So I'm going to say, starts here and then goes forever to the right. So I'm going to say that my function domain is 0 to infinity. And again, let's take a look at the range. So if we're looking at the ranges, graphs on the range. Yeah, we got some ranges here. When dealing with the problem situation and dealing with the function, remember that range is y. Remember that it's the same as the domain on the last function, on the last graph we were looking at. So range is y. I'm going to start by looking at the function this time. So looking at the function, it looks like I go down forever. I go up forever. I don't go up very fast, but I go up forever. So it looks like my range should be all real numbers. And I'm going to write that because I'm too lazy to write all real numbers. So I'm going to write negative infinity to infinity. But of course, we said that wasn't practical for the problem situation because we're not doing negative weeks. We're not doing negative time. My time starts at 0 and works its way up from there. So I'm going to say that it is from, and I'm going to put a bracket, not a parenthesis, because it includes 0 to infinity. So all real numbers greater than or equal to 0. Yay. And last but not least, does this graph have an asymptote? Yes, it does. Now, last time we had a horizontal asymptote, but now that I've done the inverse, I have a vertical asymptote. And again, it's at f equals 0. Or if you wanted to, you could say it's at x equals 0. Either way is fine with me. Oh, yeah. All right. Now that you got all this, I think you got all this. I would like you to go over to question number 15. Question number 15 on your student activity sheet looks like this. We've been playing with y equals 2 to the x, and now we've said that y equals log base 2 of x is the inverse of the function. So what I would like you to do is start by filling in this first table. That'll be easiest for you. You've got your x's here, 0, 1, 2, 3. Plug those in. What do you get? And then I would like you, remember that a logarithm is the inverse of the function. So give me the new table. Go ahead and hit pause to work these out and then hit play when you're ready to check your work. All right, so first things first, I plugged everybody in. Plug in is 0. We're good. 2 to the 0 power is 1 because anything to the 0 power is 1. I plugged in a 1. 2 to the 1 power is 2. Plugged in a 2. 2 squared is 4. And then I plugged in a 3. 2 to the 3rd power is, of course, 8. Now, remember that when you do a logarithm, do you remember it's the inverse? It's an inverse, which means I'm just going to swap my x coordinates and my y coordinates. So my x's here were 0, 1, 2, 3, but that means for my logarithm, my x's are going to be these guys, 1, 2, 4, and 8. And that means that if these are my y coordinates for my exponential, they're now my x coordinates for my logarithm, which means my x coordinates for my exponential are now my y coordinates for my logarithm. So 0, 1, 2, and 3. And all I had to do was swap these guys. Next thing I want you to do, I know 16 is asking you for something else, and we will get to that, I promise. But can you start just by plotting these points? Don't do the exponential, just plot these points on the graph below. Trust me, you'll be glad you did. Go ahead and plot these points on the graph below. Pause to plot those points and then hit play when you're ready to check your work. All right, hopefully you plotted those points because we're now going to move on to question number 16. I'm going to erase those, bring this back. So we're going to move on to question number 16. Over here. All right, so hopefully your graph looked kind of similar to this guy right here. You made a graph there on 16 and it looked real similar to this. So far, we've been playing with logarithms with a base of 2. But of course, we know exponential functions don't have to have a base of 2. Our exponential functions can have all kinds of bases, right? 5, 6, 7, 8, 9, 10, 56. I don't know. We can have all kinds of things. So here's what we're going to do. We are going to see what happens when we change the base of our logarithm. So here's log base 2, and hopefully you have a graph kind of similar to this there on page 16 that you already made. And right on top of that, we're going to sketch the graph of log base 10 of x. So let's see what happens. First of all, before I do that, here's log base 2. I can see I have a point at 1, 0. I can see I have a point at 2, 1. I see I have a point at 4, 2. So we have some very nice distinct points going on here. I think we also had a point at 3, 8, which doesn't quite fit on this graph, but you probably have it there. So what happens if I change my base? Well, let's see what happens. As my base increases, watch what happens. Oh my gosh. Watch what happens to my poor little logarithmic function. Oh my goodness. It is getting really, really squished. Oh my. So take a look at this. Here I have log base 10. So now that I have log base 10, let's see, it got really squished. Like it's still increasing, it's still doing what it's supposed to do, but man, it got squished so much from my log base 2. It still hits at the point 1, 0, but we're nowhere near 2, 1 anymore, are we? We got way squished down. In fact, I think I don't even get to 1 until I plug in a 10. I think I'd have to plug in a 10 to get a 1 out of this. So you can see it's really, really squished. So go ahead and take a few moments to graph this on question number 16. You can graph it right on top of the log base 2 of x that you made earlier. Go ahead and hit pause to make sure you get your graph in there, and then hit play when you're ready to check your work. So here's what I'd like you to do. Question 17, and sorry, because the directions for question 17 are on the bottom of the page, but then the actual problem is on the next page. So I'm sorry that the formatting is off on those. I did not make these. Question 17. I would like you to compare these two graphs that you just drew, log base 2 of x and log base 10 of x. You have this graph on question number 17. Take a look, take a look, take a look. Compare. We discussed it a little bit, but now it's your chance to jot down some notes. What do you notice about these graphs? How are they similar? How are they different? All that good stuff. So again, hit pause to write down your notes about what you notice on these graphs, what's the same, what's different, and then hit play when you're ready to continue the discussion. So there were a lot of things they had in common, right? They still had that same x-intercept at x equals 1, right? I mean, it's still the same x-intercept. It hits the x-axis in the same spot. They still have that same vertical asymptote, which is the y-axis, right? Reaches for it, but never actually gets to that y-axis. The difference, though, is that log base 2 is increasing faster than log base 10 is. That log base 10 really got squished. It's just not increasing at quite the same rate, is it? There's a little note down here on the bottom that's super hard for you to see, and so I'm going to really emphasize this. This is a big deal. Logarithms of a base of 10 are super useful in our system because we use decimals, right? We count in chunks of 10. We use a decimal number system. And so log base 10 is easily the most common log in all of existence. So because we use it so much, here's what happens. We actually call it the common log. So anytime you see a log without a base, if you just see the log of x, this is actually the common log of x. Whenever you see that, you get to assume it's log base 10 of x. Anytime you see a logarithm without a base, it's the common log. It is log base 10. Anytime you see a logarithm without a base, you get to assume that the base is 10. That is a huge, 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 huge big deal, because if you look at your calculator, if you look at your calculator, you're going to see a naked little log with no base on it. That's right. It's the common log. It's log base 10. And mathematicians are so lazy, we use that common log so much that we can't be bothered to write the base of 10. So instead of writing log base 10, we rarely write log base 10 of x. We usually write it as the common log of x. But it means the same thing. Both of these mean the exact same thing. So keep that in mind. That's super important. Don't panic if you see the base of your logarithm is missing. You now know that means it has a base of 10. So with that in mind, we're going to go over to question number 18. Yes, we are. So I'm going to make you think for this one. I'm going to make you work for this one. We've been constructing graphs. We know that the common log is log base 10, all that good stuff. So here's what I would like you to do. I'd like you to take a moment, and you may have to think about it. There is space for you to show some work and to give a little explanation over here. But I would like you to figure out, hey, what's the common log of 1? What's the common log of 10? What's the common log of 100? What's the common log of 1,000? Go ahead and hit pause to work this out, and then hit play when you're ready to check your work. So I'm going to do my explanation first, actually. Because I see that this is a common log, I get to assume that it is a log base 10. All right, common log means it has a base of 10. So if I were to write this as an exponential equation, it would be 10 to the y power equals x. So when I'm looking at this problem right here, and I'm going to make a little note of that, when I'm looking at this problem right here, I'm asking myself, hey, 10 to the what power would equal 1? Well, in this case, that would have to be, oh, sorry, my little computer's being funny. That would have to be 0. And then I'm going to do the same thing here. Hey, this is common log, so 10 to the what power would give me 10? Oh, well, 10 to the 1 power would give me 10. So I'm going to put that in there. And do that for these guys. 10 to what power would give me 100? Well, 10 squared would give me 100. And 10 to what power would give me 1,000? Well, 10 to the 3rd power, 10 cubed would give me 1,000. So I know that one was a little bit tricky, but this actually tells us something really, really, really important. I'm going to come over here. I'm also going to clear that off. Haha, there we go. This tells me something super important. If we start to bring it all together, this tells me that one of the simplest ways to solve logarithmic equations is to rewrite them as exponential equations first. So remember how in the last lesson we practiced turning exponential equations into logarithmic equations, and we even did a little bit of turning logarithmic equations into exponential ones? So here's what I'm going to advise to you for question number 19, and there's a whole bunch of these here. There's like 5 of these. I would like you to start by transforming each logarithmic equation into an exponential equation, and then see if you can figure out what x is. I promise, if you rewrite these as exponential equations, you'll figure this out pretty quick. So go ahead and hit pause to work all of these out, and it may take you several minutes, and then hit play when you're ready to check your work. All right. I don't know if you guys can hear, but Charlotte's in the background and she's really upset right now because her boyfriend is outside and I won't let her go out and play. Sorry, Charlotte, you can't go out and play. So she's meowing in the background. Sorry if you hear little extra kitty moments. In the meantime, let's solve this thing, all right? So we said to rewrite these as exponentials and then we'll solve them. All right, I have a base of 2, an exponent of x, and it should equal 8. So 2 to the x power equals 8. Well, 2 to the 3rd power would equal 8, so x equals 3. Next one, I've got a base of 2, an exponent of 8, and my argument is a -4. So I'm going to say 2 to the x power equals a -4. But I came across a problem here. There's no solution. There's no solution. 2 to the second power would equal 4, but there's nothing that's going to be 2 squared equals a -4. Like, that doesn't work. So this actually does not exist. And if you think about our graph, that makes sense. Do you remember the graph of our logarithm? We said that the domain was all real numbers greater than 0. Dude, there's a negative in there. Of course it doesn't exist. -4 is not in our domain. So yeah, that messed with us a little bit. But hopefully you caught that trick. I hope you caught that there was no solution on B there. Part C, so I have a base of 2, my exponent is 4, and my argument is x. Oh, that's easy. 2 to the 4th power is 16, so x equals 16. All right, over here I've got 10 as my base, 1 is my exponent, and x is my argument, so 10 to the 1 power equals x. Oh, well, then x is 10. Ooh, and I can't quite get to that one, so I'm going to hit the button there. There we go. So I have a base of 10, I have an exponent of x. Oh, pardon me. Yeah, no, that's right. I have a base of 10, an exponent of x, and it equals 1. So 10 to the x power equals 1. Well, anything to the 0 power equals 1. So x equals 0. Sweet. Nice. So this is a great way to solve logarithmic equations. Rewrite them as exponential equations. Once we rewrote them, these were super easy to figure out. So can we do this in other circumstances as well? I think we can. So see if you can use that same strategy, rewriting it as an exponential equation and then solving it to help you answer question number 20. Go ahead and hit pause to work this out and then hit play when you're ready to check your work. All right, people. How you doing? So first of all, log base 3 of x plus 2 equals 4. Fine, my base is 3, my exponent is 4. So I'm going to start there. My base is 3, my exponent is 4, and it should equal my argument, which is x plus 2. And sorry, it keeps cutting off the 2. I don't know why it does that. 3 to the 4th power, I have a calculator for that. That's 81. So I have 81 equals x plus 2. Again, sorry, it keeps cutting off the plus 2. Need to get x alone, so let's subtract 2 from both sides. If I subtract 2 from both sides, 81 minus 2 gives me x equals 79. Is this a solution to the original equation? Well, if I plug it in, I have a nice positive. We said we don't want negatives inside of our logarithms. We said that was bad. And that's a nice positive number. It should work out just fine. So I'm going to put my little yes in there. Boom! Look at us. We're amazing. We're magical. We're incredible. So yeah. I love this. This is a great way to solve logarithmic equations. If you're like, I don't know what the answer to that is, fine. Rewrite it as an exponential and solve it from there. Magical, miraculous, beautiful, and wonderful things happen. As always, guys, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, please feel free to email me or come see me during office hours. I'll see you later and I'll talk to you soon. Bye.